Okay. So, like I said, this is the midterm review. So the way that I normally do my midterms is they're like an assignment with a fixed amount of time. You get multiple sittings. I hate having to sit down in a dedicated block and do stuff. And it's kind of funny because teachers tend to give exams in the format that they themselves would most prefer. So I guess this is okay. I haven't had too many complaints. I did one time try to do a 24-hour exam or an infinite time exam. And what happens is students just obsess about them. And I don't blame you. People want a good grade. So we will just have a 6-hour time limit. And you can take a break, you can take a nap, you can go to bed and finish it the next morning, whatever. But just the rule is that if you're thinking about the midterm, the clock should be running. That's basically the way that I do this. And you can have access to all of the stuff, including your graded homework assignments, if you actually get them back in time. The solutions for the assignments, you can feel free to have access to those as well. And anything on the Moodle, anything linked from the Moodle is perfectly fine, but it's no collab. And by no collab, we mean you can't talk to your peers. TAs are okay if you need clarifications. I'm obviously okay if you need clarifications. Don't ask for help on the internet. Don't look for solutions on the internet, blah, 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 all that kind of stuff. You can also use your computer. You are encouraged to, unless you're one of those crazy people who actually wants to try to write IA32 assembly and not test it and turn it in. That'll be interesting for everyone involved. You are not allowed to generate IA32 assembly unless the problem specifically tells you to. But if I ever do that, it will be, here's code that I generated, now you tell me what's going on. So that'll more likely be the case. So, and like I said, it's very easy to tell the difference between compiler-generated assembly code and human-generated assembly code. And so if you're going to generate the assembly anyway, you're going to have to understand it well enough to tweak it to look like a human wrote it, and you might as well have just written it yourself. So why even bother? Okay, so I think that's pretty clear. Yeah, so if you need any clarifications, I try to be clear, which is why my things tend to be long, because I want things to be clear so that you don't have any ambiguities to sort out. If you run into any issues, please email the CS24 TAs list. I am on that list. It's going to get to somebody. And TAs may provide clarifications, but I always get the final say. So just be aware they may be wrong. So again, you might just want to email me directly if you have a question. Let's see, anything that can be covered. Basically, this is lecture 12, so anything in lectures 1 through 11 you should expect could be on the exam, including floating point, but I basically never have floating point on the midterm because I'm like, yeah, okay, it's a thing. You should be aware that it's an imprecise thing. In fact, in various projects I've done through the years and even recently, I've run into that all the time. The difference between arbitrary precision or fixed precision and just plain old floating point, not very fun. Processor structure, processor operation, low-level programming. I may have you write bits. I may not. I'm not sure. Just depends. So Boolean logic, logical bitwise operations in C, you should be familiar with that stuff. Assembly programming, there's usually at least one programming problem involving IA32. I try to scope it so that it doesn't take you like 9 hours to write the IA32 part. You probably already do the math on that one. That's bad. Flow control constructs, you should be generally familiar how to translate those things into IA32 assembly as well. And then obviously arrays, structs, arrays of structs, how malloc works, how to invoke them using cdecal, all of that kind of stuff. And then obviously all the other stuff that we've talked about. So explicit allocators and implicit allocators as well. Usually those questions tend to be higher level because, I mean, who can do any kind of real programming on these systems in 6 hours? And just as an aside, you'll notice that the midterm is more programming focused and the final tends to be higher level because we're going to be getting into systems that are large enough and complex enough that you really can't write a program for them in a couple hours unless you've been programming for a few decades like I have. So in general, things sort of get more and more sort of abstract as we go toward the end of the term. But anyway, the midterm definitely will have some programming. So we talked about this basic processor structure. Remember, we spent like the first 4 lectures talking about variations of things, like the fact that we have an instruction memory and a data memory that are separate from each other, that had a name. We called it the Harvard architecture. And we have the register file. So this is a good example of a load store architecture because we don't have multiple operands that can feed into the ALU. We just have registers that can feed into the ALU. Oops. The keys are jumpy today. So yeah, general idea that we get an opcode from the instruction and we turn on and turn off various parts of this assembly. So we tell the ALU what we want to do. Or we tell the load store logic, hey, we want to load a value or whatever. And when these values are generated from different components, we route them where we want them to go through multiplexers. Tends to be multiplexers. Demultiplexers aren't used very heavily for this kind of thing, but we have multiplexers that can route values to various locations. And so the instructions communicate with each other through side effects, either in registers or in main memory. But the instructions are small, so that's why we have to decompose our larger programs into a sequence of small instructions. It's just not possible at this level to do anything else. So typically what I do on the midterm is I will give you a variant. I might say, all right, now imagine we had two instruction. No, I probably won't do that because that's dumb. But you can imagine something like that where I'll say, here's an assembly. Now we're going to tweak it a little bit, and you tell me some details about it. We're going to explore some variation of this assembly. Okay, so question example, C code to simulate the logic that controls components. That should be really straightforward. That's just going to see if you understand your bit manipulation operations in C and can write any C code at all. Obviously, at this point, you should be able to write a lot of C code, so this is going to be easy. Simple machine code program to control the CPU. Again, I think that'll be pretty straightforward. Analyze the characteristics. That is going to be an important one. You're going to have to think about, okay, this is an alternate design. What are the benefits or what are the drawbacks of this alternate design that we're looking at? Okay. And again, just use the things that you have learned through the first half of the term to answer the questions. It really should be very straightforward. Okay, the logical and bitwise operations. Again, we have C using integers to represent true and false. This is for logical operations. So we have double ampersand, double pipe, and exclamation point, or bang, for and, or, and not. And remember that these are short-circuiting operations, which is really helpful. Anytime you have a language where you don't have short-circuiting, you get really grumbly because you can no longer do all the kinds of things that we like to do. Make sure something's not null, and then also dereference it in the same expression. You can't really do that. Erlang is a great example of a language that has, like, its and is not lazy. It has another operator called and also, which is lazy, which is always confusing to beginners. Erlang has an ugly language, but I like it a lot anyway. But anyway, and same thing with double pipe. The logical OR is also lazy. If the first thing is true, there's no reason to evaluate anything else. So the first true that logical OR hits, it stops. The first false that logical AND hits is it stops evaluating. Okay, so those are all really straightforward. Then the bitwise operations are equally straightforward. We have single ampersand, bitwise AND, single pipe, bitwise OR, tilde for one's complement inversion. Okay, notice bitwise negation, we call it, and caret for bitwise XOR. Okay, and then you have the bit shift operators, and the little nuance here is that shift right does have two versions. So you have to make sure that you are either using a signed or an unsigned value to shift right to make sure that the behavior will be appropriate. Okay, shift left doesn't care, which has some interesting nuances, but we really don't care about that at all. Okay, so shift right is the one that we really care about. And so if you want to do a signed shift right, cast it to a signed type. If you want it to be an unsigned shift right, cast it to an unsigned type. Okay, any questions about these? Yeah, this is all super straightforward. Now, typically I have, like I said, I tend to have some problem or problems, and they tend not to be too complicated because I just want to make sure that you can sit down and sort of do this on your own in some setting. So typically I'll give you some kind of problem. They almost always involve arrays of some kind because indirect memory addressing is really cool and you should be able to do it. So you'll have to either write or understand some IA32 assembly. The execution environment, straightforward. Remember, we have all these registers. You probably are very familiar with these by now. So EAX through EDX. And then we have Sp2015. Those are for stack management. And then SI and DI, which we don't really use anymore. They're for string manipulation operations, which have been around since the 8086. But Now they're just 2 extra general purpose registers we can use, so we like using those a lot. Stack grows down, don't forget about that. CDECL is one of the most important things you can be familiar with. Now I think probably it's more important that you be familiar with CDECL on assignments 4, 6, and 7 than it even might be on the midterm. But you should still be aware of all these details because you'll have to write some assembly code that has to be called from C code, and you'd like it to work properly. So caller save registers, callee save registers, and so forth. And then, yeah, stack arguments. If it's negative offset, it's a local variable. If it's a positive offset, then it's an argument passed to the function. It's really easy to keep track of, especially if you write useful comments in your code that indicate what things are. And return value always comes back in EAX. Let's see, yeah, so how to call standard C functions from my A32. I almost never have this be a requirement for the problem, but I won't rule it out, so just make sure that you are aware of it as well. This was the fun thing on assignment 3. Remember, Ben Bitdiddle called malloc and forgot that ECX is going to be trampled by malloc, and I like that problem so much. That was such a fun problem to write. So, I mean, because it's like you write good code and then you figure out, well, how can I break this to make it interesting to try to debug? But anyway, you have to be aware of that kind of stuff as well. So return value comes back in EAX and so forth. When you write IA32 programs, there's a few things that I really want you to do, and they're so important that I will probably give you points for doing them on the exam. So when I say in here, it is a good idea to ... I will probably just say, hey, you get some points if you do this so that you're encouraged to do it. It's so helpful to do. So like I say, you want to follow a pattern when you write your functions. This is what I do every single time I sit down and write assembly code. I start out documenting my arguments and what offsets they're at, because you're not going to call them A and B and Q and length and hypotenuse and all that kind of stuff in your assembly code. You're going to refer to them as some offset EBP. So why not just document what those are, and that makes it a little bit easier to translate. Also, the comments on the right tend to follow my pseudocode rather than just repeating the assembly code. You don't want to just repeat code in your documentation, because why? I can just read what the code does. So you want to make sure that your comments are useful and give you the higher level semantic meaning of the code. But anyway, you can see we always set up the stack frame. We always clean up the stack frame. We have comments in there to remind us to save and restore callee save registers. Which ones were those? Those are EBX, ESI, EDI, and EBP. Those were our 4 callee save registers, so those are the ones we need to think about. And then just a to-do for the function body. And you can put your pseudocode in here, and then you can translate it step by step, and then your pseudocode becomes your comments. Okay. So this is a very helpful thing to do, and I strongly encourage you to do it. Do not sit down and just blank screen try starting to type assembly code. I mean, this is 2015. We don't have to do that anymore. So save yourself some effort. Okay, so yeah, this is the setting up and this teardown of the stack frame. If you remember, you don't have to do this. If you have a really simple function, then you don't have to set up and tear down the stack frame. Now, I almost always give you a more interesting function to write for the midterm, so you probably will want to do this, but just be aware that the compiler will frequently try to leave this stuff out if it possibly can, because it's instructions. It's slower than not executing instructions. So, but we generally will need to do this. So it's always a good idea to leave it in and then maybe remove it in a subsequent transformation step. Let's see, figure out where the arguments are stored, and yeah, don't forget that CDECL pushes them in reverse order. So again, 8 EBP will be your first argument, 12 EBP will be your second argument, and so forth. So I think I actually have an example of this. So vector add. The arguments were A, B, and length was pushed first, so it had the highest offset because the stack grows down. So then B is the second thing, and then A is the last thing. So it's going to have the lowest offset. Okay, questions? Do you have a question?
Is there a convention whereby you're supposed to take the variables, those, and store them in registers? Or is just referencing them that way all of the time?
That's a really good question. Is there a convention? No, not really. Is there sort of good practice? Kind of, maybe. It's a really hard call. And the reason why it's a hard call is because the processor is so complicated inside. Because sometimes if you can have instructions that directly reference memory, then the memory accesses can be pipelined with other operations that may be interspersed with those memory accesses. And so sometimes you want to use them directly. But other times, like if you refer to a value, like an argument, more than I would say twice, then I would probably stuff it in a register, because using it from the register is going to be much, much faster. In fact, we're going to start talking about that on Wednesday and Friday. Why we like to move stuff into registers and not just access it directly in memory. So that is not really convention, that's just a suggestion. Yeah?
So if you have a pointer if you're past a pointer and you need to dereference it, you need to put it into a register.
Yeah, that's a great example of something where you would have to store it in a register. If you have a pointer stored in the stack and you need to do indirect addressing from it, or you need to just access the value that it points to, then yeah, you need to pull that into a register so that you can do an indirect access. Now, crazily, if you are past a pointer to jump to, you don't have to do that, because there's actually a mechanism for indirect jumping on IA32. But I basically never have anybody do that, because that's crazy talk. You know, hey, here's a pointer, jump to the code there. Trust me, it'll be fine. So, but yeah, in general, if you are passing a pointer and you need to manipulate the values at that pointer, then you'll need to pull that into a register anyway. That's a really good observation. Okay, anything else? Alrighty, let's see. Yeah, so it's easiest to write the function body in pseudocode. So I will probably make you write pseudocode for one of the steps of the solution and turn in your pseudocode. It will also help the TAs understand what you're thinking when they have to grade your exam. And like I say, there's really no point in writing the save callee save registers and restore callee save registers parts until you actually know what callee save registers you need to modify. Historically, there was a terrible exam problem which I never use anymore. It's even too much for a homework assignment, but the problem used one more register than the total registers you actually had to utilize on the processor. And so inevitably, you'd have people doing all these crazy pushes and pops in the code to try to save things and make space for all of the values that they needed to manipulate. It was terrible, so that problem has been banished. But so in general, you probably will need to touch a few callee save registers, but it won't be horrible. I try to give you problems again that are reasonably scoped. And yeah, EAX is going to contain whatever the return value is. Okay, C-flow control. Again, you need to understand how these are implemented in IA32 assembly. It's really straightforward. Remember, all the translations were really simple. If you can do in a number of different ways, depending on if you have else if or else or whatever. For loops are just while loops plus a little bit of extra. And while loops we can turn into a do loop plus an if for the first test to decide if we need to skip the entire thing. Okay, and so like I say, almost always what you do for these problems is write the pseudocode and then go through a series of transformations to turn it into IA32. It's what the compiler does. The compiler doesn't just start generating assembly code right off the bat. You might as well do it too. And like I say here, the conditional jump operations are based on E flags register. So carry, sign, overflow, and the zero flags are the ones that we really always care about. Okay? Very helpful to understand exactly what these things mean. Remember, the sign flag is just the topmost bit. So if it's 2's complement, then that sign flag will say, hey, it's negative or it's not negative. The sign flag will be set whether it's 2's complement or not. So if you just have a really large number where the top bit is set, the sign flag will also be set, but it's unsigned, so you can ignore it. Okay? So you just need to understand how to interpret these things. Carry flag, same thing. You may do a signed arithmetic operation and the carry flag gets set. Doesn't mean that there was an overflow. You need to look at the overflow flag because that's signed overflow. The carry flag only indicates unsigned overflow. So just make sure you understand all these little nuances. The zero flag is the easiest one. If all the bits in the result are zero, the zero flag is set. Okay, that's basically all you need to think about. Okay, so arithmetic and logic operations, update E flags. You can also use compare and test, which I love, 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 so you can be sure that those are going to make an appearance. If you're going to write a loop, you need a comparison so that you know when to leave. So compare source 2, source 1 updates the flags as for source 1 minus source 2. And test is very, very helpful. You'll see it from time to time. It's sometimes it's even used for little shortcuts. I'll point out a shortcut in a slide or two. But yeah, that'll be as if you bitwise ANDed source 1 and source 2. Okay? And then those registers are not modified, or those arguments are not modified. And you can specify size prefixes if you prefer. And the one thing that's annoying here, and this is why it's in the midterm review, is that the AT&T syntax mucks up the clearness of the ordering of these operands. Okay? So source 2, source 1 is as if you did source 1 minus source 2. Source 2, source 1 is if you did bitwise AND source 1 and source 2. Not that that matters with bitwise AND, but it clearly matters with subtract. Now the reason why I wanted to mention test is that you can test something against itself. And it seems a little bit weird why you would want to test something against itself, but remember, this is a great way of sort of figuring out what the characteristics are of a value just by looking at it. Because what it does is it sets the sign flag, it sets the 0 flag. The carry flag doesn't need to be modified by this, and the overflow flag won't be modified by this. But you can see here that if you have this value in source and you want to see if it's negative or 0 or positive, you can use test to set the flags, and then you can do the appropriate thing. So sign flag is 1, the value is negative. Obviously, the 0 flag will also be 0 in that case. If the sign flag is 0 and the 0 flag is 1, the value is 0. In fact, who cares about what the sign flag is in that case? And if both of these are 0, then you know the value is positive. Okay? So you'll sometimes see, like the compiler takes advantage of this kind of thing whenever it can. And you can as well, if you know how to use this stuff. Okay? Questions? By the way, you should also be familiar with how to specify constants in hexadecimal and so forth, because you may need to be able to specify constants in assembly code or in C code or whatever. Okay? Again, not complicated. 0x and then whatever. It's really not that big a deal. Okay, for loop, let's just go through this really quickly to show you how it works, or I should say remind you how it works. But this for loop is a while loop with extra initialization. So we say I is 0 up front, and then we turn it into a while. So for loop tests its condition before the first iteration of the loop, so that's why it's like a while loop. And then we have the update part at the end, I++. And yeah, and again, this is what I will strongly encourage you to do, and I'll even give you points for doing it, is start out with the clear pseudocode version and then translate it into assembly code in multiple steps. Don't just start writing assembly right away. Okay, once we have a while loop, we can turn it into a do while by pulling off the first test. Remember, so now we have I is 0, and we invert the test, so if not I is less than length, then we jump over the for loop. Okay. And so we can also say if I is greater than or equal to length. That's the way we had it in the previous lecture. I think it was lecture 7. And then we go ahead and have our do while. And so at the end, if the condition is no longer true, we just fall through. And we prefer this approach because we only have one conditional operation in the loop, not 2. And that's much cleaner. I shouldn't say one conditional operation. We only have one jump, not 2. Because one was an unconditional jump and the other was a conditional jump. All right, any questions on this transformation? Hopefully this is like, yeah, this is easy. If it is, awesome, you're going to do well. Okay, compare. So this is where I had, if not I is less than length or I greater than or equal to length. And what I was saying in that lecture is just reverse the operands to compare, because then the conditional jump instruction will match whatever you have in your pseudocode. And that'll make it a lot clearer. Okay, so if I'm saying I greater than or equal to length, then I put length first and I second, and then I can say jump if greater or equal, okay, as opposed to just trying to figure out some other way of expressing this. Okay, so yeah, that's sort of my big hint, because comparisons are annoying enough. Now there's also important to understand that there's signed and unsigned comparisons. So greater, less, above and below. Above and below are unsigned, and greater or less are signed. Is there any sort of fundamental reason why they chose greater and less and above and below? Probably not. I've been on enough software engineering projects by now to know that usually people pick stuff because it just seems like a good idea at the time. And that's probably what happened here. Unless there's some fundamental definition of greater and above that I'm not aware of. But anyway, just be aware of that. And again, on the exam, I'll tell you if stuff is signed or unsigned. So you can just know what you need to do. Okay, let's see. Yeah, so IA32 has all these arithmetic and logical operations. Yeah, so the thing that I want to mention here is just the source and destination. We already kind of talked about this. The source can be a value, it can be a register, or it can be a memory access. And the destination has to be writable, so it can be a register or memory access. It cannot be a constant, as is obvious. And both arguments are not allowed to be memory access. So one of them can be a memory access, the other one can be a memory access, but that's it. Now the one weird caveat to this is that I think you can actually push or pop something based on an indirect memory access. I can't remember. Somebody might have to remind me if this is true or false. But it's accessing the stack, but you're accessing the memory as well. So it's kind of weird. I think you may actually be able to work around that limitation just for pushes and pops. Not that it'll matter at all. Anyway, yeah, so IA32, multiply and divide. And again, I don't like using these, but again, you may run into them on an exam. So signed multiply, unsigned multiply. And mul is the easy one, because remember, it multiplies two n-bit values and produces a 2n-bit value. So AL by the operand goes into AX. AX by the value goes into DXAX. EAX times the operand goes into EDX EAX. Okay? So that's the way that mul works. And remember that mul is unsigned. I in front of it means it's a signed multiply. I don't know why they didn't do smul and stiv. I don't know. That might have been a little clearer that it's signed. But anyway, imul has all these weird operand formats. We have one operand, two operand, and three operand forms. And so you can actually have three argument mul, where you say multiply this by this and store it somewhere else. You can definitely do that. And the two argument form is I think EAX times the first argument goes into the second argument or something like that. You can go back and read the slides about it. Okay, IA32, division instructions, so signed and unsigned division. And these only take one operand because they take an n-bit value and produce an n over 2-bit result. So whatever the argument is, divides AX by the argument, or DX AX by the argument, or EDX EAX by the argument, produces a quotient and remainder. Okay. Yeah, so quotient will be in EX, remainder in EDX. And don't forget there's all those convert, what was it? It's there were all those weird little instructions that you could use to expand. There's convert a byte to word, or convert a word to a double word, or a double word to a quad word, to set up EDX, EAX for those kinds of things. Okay. By the way, who has looked at the lecture recordings page? Can I see a show of hands who's looked at the lecture recordings page? You may have noticed that the lecture recordings page has a list of what each lecture sort of talks about. So, really useful tip, if you happen to be doing the exam and you run into some topic and you're like, oh, I don't remember what this topic is, just go to that page and search for terms that might match what you're trying to do, and then you can go straight to the lectures that have it. So hopefully that's useful. Tell me if it's not, because that's the whole reason why I write the stupid index on that page, is so that people can look stuff up easily. I want it to be easy for people to find information. Okay, so that's enough about multiply and divide. And the only reason I mention that is because there's a lot more detail on multiply and divide that you could go into, but we don't talk about it just for the sake of time here. Let's see, arrays in C and IA32, very important to understand. So you have an array declaration like this. Remember that every element in the array is the same size. We can find out the size using size of. And so we can have a declaration like this. A will be a pointer to a chunk of memory that is the appropriate size. And so like you see here, it allocates n, the number of elements, times the size of the element type. That many bytes for the array will be set aside for that array. And so the variable will hold a pointer, and there's an equivalence between pointer math and array indexing. And when you add a number to an array pointer, it moves it forward or backward based on the element size, not just the number of bytes you want to add in. So a plus 5 is not going to move you forward 5 bytes, it'll move you forward 5 elements. Now obviously if elements are bytes, then it'll move you forward 5 bytes, but if elements are D words, then it'll move you forward 5 D words. Okay? So just make sure you understand all those details. Are there any questions about arrays? If you get into situations like an array of structs, how would you deal with an array of structs? Well, that's where you might need to think about LEA. LEA can be your friend because what you can do is you can use LEA to compute parts of the address, the addressing, and then you can use that as part of the indirect addressing. So you can think about all of those kinds of stuff. I like arrays of structs. Hint, hint, hint. So just think about that. Multi-dimensional arrays, all that kind of stuff is fun because it sort of really exercises your indirect addressing understanding. Okay, of course, memory addressing, as long as you have just a single dimension array, then it's actually really straightforward in IA32. This is a very common situation. I have a character buffer, something like that. So you have index memory addresses where you have a register with the base address or that A, the starting address of the array in there, and then the index, and that'll index based on elements being bytes. You can add a constant in that as well. Okay, again, assuming that the array elements are bytes. And then you also have the scaled indexed memory access. And remember that scale can't be just anything. It has to be 1, 2, 4, or 8. Which is, again, presuming that the array's elements are 1, 2, 4, or 8 bytes. It's very, very common to have that scale be 4 or 8 if you're accessing an integer array or a float array or a double array or a long array, something like that. Okay. Or should I say long, because I think in GCC it's long. Okay. Any questions on these addressing modes? Again, be familiar with them. That'll be very helpful. This was the summary chart from the IA32 manual, which I think is great. And this is basically what the indirect memory addressing can do, and also this is what the LEA instruction can take. Because remember, LEA does a lot of this stuff for you. So base register can be any of them. Index register can be anything but ESP. Don't know why. I'm just really curious. There's got to be some reason why not ESP for that one. I don't know how much logic was necessary to say not ESP or how much logic was saved to say not ESP. But anyway, the scale can be 1, 2, 4, 8, and then you have a displacement as well. Which the size of the displacement is not relevant to us. That's really more important for the instruction encoding, but we really don't care. All right, enough of that. So a vector add function loop. So we had this. Remember, we accumulated each value into EDX. So we move the first array's element into EDX. ESI was our index. So EBX had the start of A. ECX was the start of B. EAX was the start of the result. And then ESI was our index. And so we could just do scaled index addressing, and it was super easy. Okay? And we just accumulated into EDX and then moved that value back into the register. Okay? All right, I just said all that. So no questions? Good. This is really encouraging. I hope you all do really well on the exam, because obviously if you guys don't do well, then it makes me feel like, oh, maybe I should explain this better. Let's see, yeah, so addressing mode, yeah, structs as well. So we had this example from lecture 8. So just as a reminder, what is the size of this struct when we ask the compiler what size the struct is? Somebody say it loud enough for me to hear. Yeah, it's 12 bytes. Even though we only have 4 bytes plus 1 byte plus 4 bytes, that's 9, but the compiler tries to respect data alignment because we know that aligned access is faster than unaligned access. So, like here, if S1 star S is stored in EBX, then SI is going to be just give me the value at that address. CH is going to be, notice, move B. That's the little key here. If you happen to have a problem like this on the exam and you're not getting it to work right, you may have forgotten and done a move L instead of a move B. Now, if you do a move L and say CL, then it's not going to work. But, thankfully the assembler is intelligent enough to prevent that. But if you're accessing a byte value from a struct, you need to actually use a byte operation, a byte move or a byte add, so forth. SJ, I think you're all really familiar with that from assignment 3 because that the run length encoding problem kind of beats that one to death. Okay, so anyway, very straightforward, right? Unions would be very different. Unions would be all like move L EBX, move B EBX, move L EBX, and so you'd need some tag to sort of tell which one was actually the correct one to use. Okay, so any questions about any of this stuff? No? Okay, cool. Then the last part that I'm going to talk about, and we may actually get done really fast, so if I'll give you guys a chance to ask any other questions you might have. But explicit allocators, remember the program is responsible for allocating and freeing memory. And I spent a lot of time talking about these things in class, so I'm kind of optimistic that you all will understand all of the details here. Remember, fragmentation is an issue that can occur over time where the memory amount is available, but it's all fractured and spread out. And fragmentation is a great thing. It's fragmented in the same way that a glass would become fragmented if I threw it on the ground. And now, yes, all the pieces of the glass are still there because physics works, but it's not a glass anymore. It's a bunch of little pieces. So you don't have the amount of memory that's necessary to satisfy the allocation request. And think about all the different scenarios that can happen with a program running. I'm allocating always the exact same size chunk of memory and freeing it and allocating and freeing it. Well, I never have fragmentation. I allocate size 1, blah, 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 blah. I allocate a whole bunch, and then I free it all. I allocate size 2, blah, 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 and then I free it all. Then I add back to size 1, blah, 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 blah. That's also not going to generate fragmentation. It's when you allocate different size things, and then they have different lifetimes. And so some of them you free, and then other ones you start to allocate, and they're slightly different sizes and so forth. And what happens is the allocator is trying to figure out where to place these things, and it has no idea what your program is going to do. Your program may not know what it's going to do because it may be getting data off the internet or something and saying, oh, I need this, I need that. So fragmentation happens. It just can happen. Okay? So just be aware of that. So yeah, heap, I already showed you this example before, and now there's only two 1 kilobyte chunks, not 2 kilobytes. And we can't shuffle things around because typically in explicit allocator land, we have pointers inside of these things, and we have pointers to the inside of these things, and we can't shuffle them around without having to go and update all the pointers. Okay, coalescing. So we can certainly do that. Remember that false fragmentation is a thing. False fragmentation is usually a bug, not just an unavoidable characteristic. So if you have an allocator with false fragmentation, it just means the allocator hasn't been written to be smart enough and it needs to be improved. Okay? So false fragmentation you almost never really need to think about. There's a whole bunch of different placement policies. And yeah, so in this example, we want to allocate 1 kilobyte. You can see that there's 2 different free blocks that we could choose. Which one do you prefer? Well, it really only matters if the program later decides to allocate 2 kilobytes. If the program will only ever allocate 1 kilobyte chunks now, then we don't care. So, but where would be best fit? Yeah, it would be the last one, right? Because that would exactly satisfy the requirement. First fit, if we're going from top to bottom, then first fit would break that 2 kilobyte chunk into 2 1 kilobyte chunks. And remember, we also have this weird next fit thing, which we usually don't talk about, but next fit just resumes searching from where I last stopped looking. Okay? So, which kind of makes sense, because if you have a big pool and it's all free, and you allocate a little chunk, and then you just want to start looking there, and you allocate a chunk and so forth. So next fit's probably always going to point to a big chunk of available memory that you could just chop into pieces. Okay, let's see. Yeah, now I say first fit policy would cause memory fragmentation. That's too strong an assertion. First fit policy would cause memory fragmentation because it kind of presumes a certain behavior of the program. But I suppose that it is more fragmented, having 2 chunks of free memory is more fragmented than having 1 chunk of free memory. So, but yeah, you just have to think about that kind of stuff. Okay? Implicit allocators, a lot more fun. Oh, and I do mention here buffer overflows, exploits, that kind of stuff. I may sneak a security problem onto the exam just for funsies. Here's a program, figure out how to make it do something horrible, or what kind of things could make it do something horrible. Can you prevent them? Blah, blah, blah. So you can think about that kind of stuff as well. We don't talk about it in great depth. We just talk about it a little bit at the end of our explicit allocator discussion. So don't spend too much time thinking about it. Just understand CDECL and you'll be fine. That's really, we don't go into things like, there's actually a whole book, which I think I have a reference to in the additional reading section. I can't remember what it's called. What is it called? Well, I have a copy of it in my office, so if it's not listed there, then come by my office and I'll show you the book. But it basically goes through all the ways in which you can target programs and try to compromise them. And, well, you don't want to understand these things to be a jerk. You want to understand them so you can prevent them and write more secure software. But, that caveat aside, it's a really interesting topic to understand. But it's way more involved than what we talk about in CS24. Okay, so yeah, the whole idea is let's get rid of all this power because people don't need it. So you get rid of pointers, you get rid of pointer arithmetic, you get a new opaque reference type that you can you can manipulate it, but in very limited ways. And then use an implicit allocator so that you don't ever have to deal with programs not freeing stuff and you thinking the memory's still in use. So we instead have garbage collection. And we had these 2 examples of mark and sweep versus stop and copy. Okay? And so there may be examples of that on the exam as well. It's pretty straightforward. I'm not going to spend too much time talking about this stuff because obviously it was one of the most recent things that we've done on an assignment, so you've got pretty recent exposure to it. But you also have these other abstractions that we have as well. Object-oriented programming, exception handling, set jump, and long jump. And set jump and long jump are crazy, but they all still completely work within CDECL. So, again, CDECL is your friend. If everybody follows it, you can do some pretty awesome things. Okay? And so we have this alternate flow control mechanism via set jump and long jump. Okay, and so yeah, there may be other things that are related to these topics. They're not going to be particularly deeply involved. I generally focus on like the first 2 to 3 weeks, but there may be a few problems about this kind of stuff, so it's good to know about that as well. Okay, now any questions about this stuff in particular? Because I actually don't have too much to talk about left. I'm going to be starting to put together the midterm this week. And I will probably be releasing it Wednesday evening to Thursday morning, depending on how my life goes. So we'll see how it all goes. But it will be due basically when, the next assignment would be due. There will not be an assignment during midterm week because that's really cruel. I hate doing that. I hated it when I was a student, so I'm not going to do it to you guys now. But anyway, Thursday, May 7th, 2 a.m., as per usual. You are allowed to use late tokens on the midterm. And the reason I say that is because you are not allowed to use tokens on the final without letting me know and getting my approval first. And the reason why is because the registrar is super nice to me because some of those people were there when I was an undergrad and they still really like me for some reason. But when it comes to getting grades in on time third term, especially senior grades, they start threatening things like cutting off digits, killing my pets, burning down my house if I don't get them in on time. And for obvious reasons, like seniors have to actually be approved by, I think, 2 different committees before they graduate. So that's why we say no late tokens on the final without my personal approval. So anyway, the solution sets will all be available. I'll get the assignment 4 solutions out pretty soon. It's due this week, so I won't probably release them until Friday afternoon. But anyway, all of that stuff will be available. Don't go yet, because I have one last thing. Since we do have extra time, is there anything that anybody would like me to go over in more detail as far as topics for the exam? Okay. I mean, it is pretty much exactly as I represented. You'll have to do some CPU stuff, like basic stuff like assignment 1. You'll have to do some IA32 programming. Straightforward, but a little bit complicated. Certainly not 6 hours of assembly programming. And then maybe some higher level discussion of allocators and exceptions and set jump and other stuff like that. Okay, that tends to be the way the exams go. Okay, so any questions? All right, then good luck. We will pick up on Wednesday our next topic. So please come; it'll be fun.